Yeah, that's a really good possibility here. And one of the extensions of these models, as you said, is really to detect other objects, not only clouds. In a sense, like clouds are a bigger challenge than detecting other objects.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Adler Santos. He is the managing engineer at a company called Skywatch, and he's building a machine learning algorithm to detect clouds. So immediately you might be thinking, cloud detection, whatever, we can do that already. But I think after listening to this podcast, I think that you'll agree that it's a really difficult and important problem to solve. And of course, we'll get into some more details around that during the episode. This episode is sponsored by landgrid.com. So this is your go-to resource for parcel data, for property boundary data for the US. They have plans to extend it to other territories, but for the moment, it's just for the US. So if you need property boundary data for the US, if you need ownership data for the US, land use data for the US, landgrid.com is the place to go. There's lots of different ways you can get at the data. They have an API, they have a tile server, they have a data store where you can bulk download for individual counties. And there's also a few free options there on the website. So on the website, landgrid.com, you can click and for free get access to some of this data as well. They also have a free mobile app, which is perhaps worth checking out. Okay, that's it from me. Let's get on with the interview. Hi, Adler. Welcome to the podcast. Thanks for taking the time to talk with me. And today we're going to be talking about cloud detection, and towards the end of the podcast, or the end of the interview, I should say, we're going to tie this into programmatic access to satellite data. And before we jump into all that interesting stuff, maybe you could just give us a brief understanding of your background, where you come from, how you got involved in this.
Yeah, sure. Thanks for having me, Daniel. So I'm currently the engineering manager for TerraStream, which is a product of Skywatch, and it's a data management and distribution platform for satellite operators. So just to give you a bit of a background, my education is in physics, and my graduate thesis was about polarization optics. It really ties well into this satellite imaging technology thing, where it's really all optical technology right from the start. Like, my experience also translates well to machine learning, which made me end up here, where right now I'm detecting clouds on satellite images.
Okay, so we understand that you've got a really good background in this, in machine learning, and now you're applying it to cloud detection. We're talking about satellite imagery here, and I think it would be really interesting to understand why cloud detection is so important. Why do we need this? I mean, can't we just look for all the bright pixels, say all of your bright pixels, if they're all white, you're a cloud, and move on?
It's not as simple as that. Like, why are detecting clouds important? It's because most of the value gained from satellite images are actually based on what you can see on the ground, which means that if there are cloudy images, you won't be able to see what you need to see on the ground. And that's the goal of cloud detection for satellite imagery. It's to ensure that when you order the images that you want, they're going to be as cloud-free as possible, and you can just go directly right on into extracting insights or applying analytics on those on the data.
Okay, so I apologize for baiting you a little bit there. And I'm sure a lot of the listeners of this podcast will understand that, if we put too much water vapor in front of these satellite imaging platforms, that they obscure the surface of the Earth and make them kind of redundant, because that's why we put them up there, is to image the surface of the Earth. It's kind of interesting to think about the amount of resources we pump into this as an industry, and then again, too much water vapor in front of the imaging sensors there, and we lose all value in the platform. So we're competing against the weather in essence, I guess. And I appreciate you for clarifying that for us. Why is this a difficult problem to solve? I guess that's my next question.
It's a difficult problem to solve, one, because it's really mainly a matter of convenience. So the traditional way of ordering satellite images is, okay, you're going to search for an AOI, let's say of New York, and then at this time and at this date and so on. And then before you order that, you're going to be offered the image previews for that. Like, okay, so this is approximately how it's going to look. Usually what people do is you eyeball the image previews before you actually order them, which means you just take a look at them, make sure they're clear, like the AOI has a clear line of sight. And then after eyeballing that, and then you can quickly determine if there are clouds or not, and that will let you decide whether or not you should order them. Now, take note, this is all manual, right? So what happens when you need to order hundreds or even thousands of images regularly? So I think I'm going back to that point where it's really a matter of convenience, because it's going to be more efficient to have a programmatic way of determining whether or not those images are cloudy. And this leads to, I guess, a programmatic way of ordering and detecting insights from these valuable data.
This is really interesting to me, because whenever I think about the satellite imagery industry, or when I think about Earth observation in general, it seems, so high tech. And yet you're telling me that when we take these images of the Earth's surface, and it doesn't really matter if we can, image a area of the Earth almost in real time, or multiple times during the day, we can't actually get access to this data easily. At least that's what I hear you say. It sounds like an incredibly manual process. So that's a bit of a revelation itself, at least for me. But again, the question here is, why is it difficult? Why is this a difficult problem to solve, to detect clouds?
It's a difficult problem because, first of all, there's just so many ways that you can represent or even misrepresent clouds on satellite images. As far as I know, I'm confident to tell you that cloud detection on satellite imagery is still a very open problem. I know there are lots of papers that are going out right now, but there's no real single way of detecting clouds. Everyone has their own approaches. Every model has their own things to look for, features to look for, or even aspects of the data that are not yet considered. So in a way, this is a very open problem, which makes it difficult to solve when you're trying to actually build a model that tries to span a wider range of satellite sources or satellite data.
Okay, so with my humble background in remote sensing Earth observation, I know that there's some spectral bands that are really reflective when they hit water vapor. Can't we just use some of those bands and say, okay, well, if they're reflecting strongly, that is a good indicator that there's some clouds there, and just apply that to satellite imagery in general?
Yeah, actually, that ties well to a question we often get. So, some satellites, they have bands that specifically detect clouds. These are usually called cirrus bands. So why not just use them, right? Here's a simple answer. It's because not all satellites have the cirrus band, and not all satellites are capable of detecting that, which means that there are only very specific satellites that can detect that. Now, what if you want satellite imagery from other sources that don't have that, right? So you need some sort of way, some sort of automated mechanism to detect clouds from sources or satellites that don't have cirrus bands.
Okay, so what bands are we using now? Are we using the RGB bands?
That's right. Currently, the cloud detection goal that we have right now is to try to answer this question. How can we build a model that can be used across different satellite images coming from different sources with the least amount of bands? Now, in order to build a model that can span the widest range of satellites, you have to remember that every satellite will have their own distinct set of bands, right? For example, let's say Sentinel-2, I think, has 13 bands, Landsat-8 has around 9 bands, and so on. But there's always going to be some sort of least common denominator in all of them. And we found that the RGB bands is a very good set that fits almost all of the satellite data that we have.
Is that simply because, obviously it's a massive advantage of those bands are present on lots and lots of different platforms. I completely understand that. But is there anything else about those bands? Is it the resolution that they come in? Is it just the fact that we could perhaps, eyeball those images ourselves and do ground truthing in that way? So run our algorithm and see what it comes up with, and then have a human look at it and say, okay, yes, that looks like a cloud. That's not a cloud.
That's right. Yeah. Most of the applications right now are still going to be from optical images. So optical images means, as you said, these are just the RGB bands that everyone is familiar of. And also, it's not like all of the analytics now are able to leverage or are capable of trying to use so many more other bands. Most of the analysis that's taken from satellite images right now are analysis that can still be done with the naked eye, which means these RGB bands are still going to be very useful up to today.
Does this also mean that you can take advantage of previous work in the sort of object detection space? Because I know, for example, there's lots of face detection algorithms out there. There's algorithms that can detect cats and dogs and houses and other objects, and they're all running on the same sort of optical or RGB bands. Can we take those algorithms and simply apply them to satellite data?
That's actually one of the big challenges in trying to apply neural networks to satellite images. It's as you said, I guess the simple answer there is we can't really use those models. We call them pre-trained models, by the way. So nowadays you have these collections of pre-trained models that you can just download from the internet, right? And then you just fine-tune them to your liking or tweak them based on your use case. So like, as you said, typical use cases are face detection, cat or dog detection, and so on. And then off you go, right? Most of these models are openly available to everyone, but the fact is they're trained using data that's not representative of the top-down view that every satellite can see. These images, like they're very conventional. They're stuff that you see every day and that you can usually take with a conventional smartphone or camera, right? But satellite images and the ones that they see on the ground, like a very, very high resolution and on a very top-down approach, has a very different profile and representation of the data.
And is that, just so I understand this is simply because we're viewing these objects from the top down, which makes sense, from space looking down at Earth, and we're simply seeing them, or we're not seeing them, I should say, at different angles and at different resolutions. Is that what's making the difference here?
Yeah, that's right. So for example, I'll give you an example for a conventional model that you can download from the internet. So every model needs to learn very different features. And every model needs to aggregate all of these features so that it can ultimately arrive at a decision whether it's seeing a cat, a dog, or even a table, let's say. Okay, so for example, it wants to detect tables, right? So tables have these very sharp edges. So for a pre-trained model that's trained on these images, it's going to interpret these sharp edges as probably tables, or let's say other sharp curves or edges that you see in daily life, right? But for satellite images, what translates to sharp edges? It could translate to, let's say, roads, road crossings, and it could also translate to rectangular shaped buildings or rectangularly shaped objects on the images. And that might translate differently from what all these pre-trained models are trained on. So yeah, there's quite a difference. I usually use the term corpus to just differentiate between the features that satellite images have and the features that everyday normal objects have.
Yeah, I can see a few other things here. I'm just sort of thinking out loud here. Like for me, clouds could be discrete objects. They could be continuous objects. I could imagine, for example, it'd be really difficult to detect clouds and distinguish between clouds and smoke or snow or simply other really bright reflective patches of the Earth's surface. And I'm assuming clouds, they come in different at different altitudes, different sizes. Yeah, I can see this being a real problem. And I think too, when we talk about face detection, so I'm pretty sure I could go to the internet and find hundreds and thousands of images that were already tagged as a human face and download them. And I'm assuming that would make, probably a pretty rough training set, but a training set nonetheless, because someone had done the work for me. They've said that somewhere in that image there's a face. Is this the same way with cloud? Like, can I get that kind of stuff with clouds? Can I go and find a database of pictures of clouds?
That's actually very true. And that's a very valid challenge that we have actually up to this point. It's the challenge of how can we get as much data as we can in such a way that we can source them from open data sets, right? As you mentioned, like all of these pictures of cats, dogs, billions or millions of them, you can get it very easily from the internet. But satellite images, you could probably get some of them, but they're very low resolution if you want to get them from open data sets. Now the question is, how can you get like more and more of them? Let's say very high resolution and from multiple sources and so on. So all of these things, you have to take into consideration the commercial aspect of it, which means that if these are commercial data sets, they're mostly not going to be openly or freely available on the internet. You have to have some way of sourcing them, probably internally, probably from partnerships, probably from integrations. And on top of that, you also have to know the policies around that. can you use this image from this provider, or can you use that image from this other commercial provider? Can you use those for deep learning applications? Can you use those for analytics? So all of these things we all have to consider when preparing the training data.
Okay, but let's assume we have some training data. So somewhere along the line, somebody has gone through a bunch of images and tagged them as cloudy, not cloudy, or maybe, marked the areas that were full of clouds. So we have these images there. So typically when you're doing image segmentation, or in terms of Earth observation anyway, we can use other data in the background and we can start building up these a signature. Do you have the opportunity here to use other data sets? I'm thinking about global weather models, for example, and because when the image was taken, where it was, and if you had a global weather model, you could say, well, was it cloudy there at that stage? Is there any sort of opportunities there?
Yeah, that's a really good question. One of the things that are actually in our roadmap is to explore all of these alternate data sets. So it's not only pixel data that you care about when you want to predict something, whether it's cloudy or not. Other factors can come into consideration. Like, let's say there are two outstanding factors that we're thinking of. One is the weather prediction around that area. So again, let's say you want something, you want a satellite image in New York, and then you need it sometime like maybe 3 days from now. So instead of just having to wait for the satellite to capture that and then try to run your algorithm as is on the pixel data, you might as well check the weather forecast in that area in advance, right? That could very well be a very good indicator of cloudiness in that area. Another thing is that we're exploring is the altitude. Not all objects on the ground have the same altitude. So let's say you have a higher altitude, which means that there might be a chance that it's more cloudy or maybe less cloudy. We don't know. But it's something that's worth exploring. Yeah, I agree with you.
So let's assume we have our test data and we're going to sort of drag in some of these other data sources that we've been talking about. So it sounds like it's going to take a little bit of momentum to get the ball rolling here. But once we get an algorithm that's, making accurate predictions, is this something that can feed on itself and we sort of add to that training set as we ingest more and more data and run the model more and more times?
Yeah, that's right. Most of the challenges that we face when it comes to accuracy is not so much the model, but so much as how large your training data is. But of course, that's there's also a case of the larger your training data gets, the longer it might make for you to train the model. One of the big challenges in training the model is the performance. Why? A single satellite image can span from dozens of megabytes to even a few gigabytes in size. So when you're thinking about probably like thousands or hundreds of thousands of images, your training data can blow up to, say, terabytes in scale or petabytes in scale. And that could lead to very, very long training times. That could also lead, there's also cost considerations, right? So in a sense, more data will mean better accuracy, but you also have to consider the length of training that you need to do in order to deploy before you can deploy these new versions.
Let's just stay with the size of the images that you're working with just for a second here. Have you found when you've been running your model that you get almost the same results from lower resolution images as you do from higher resolutions? There must be some kind of break-even point there where the results actually don't improve no matter how high the resolution is.
Yeah, you're right. But I guess in terms of accuracy, the one thing that we found to have such a large impact is the resolution, like the variety of resolution that you have. Let's say you train a model only on low resolution images. You're probably going to get a very high accuracy, but only if you feed that with low resolution inference images, right? And the same goes for very high resolution images. I have the same analogy here where if you train a conventional model with like dogs and cats, like some dogs are far out there and some dogs are like just right in front of the camera, right? Same with cats, same with other objects. So it's the same thing with satellite images. For clouds, you can detect them on very high resolution and on very low resolution, only depending on like the variety of resolutions that your training data has.
So in terms of running this model in the real world, so if this is going to be useful for people, it needs to happen relatively quickly. At least that's what I'm thinking. Do you have any sort of target times for running an image through the model and getting a result?
Yeah, that's a very valid consideration. So when we started out building our initial version of the model, it took around, I think, 5 to 10 seconds per image, and it was not as performant as we expected it to be. It was because mainly of the way the algorithm works behind the scenes. So for this initial version, we were using semantic segmentation. So if you don't know, so semantic segmentation is a way for us to label every image on a per pixel basis, which means that if you have an image with clouds on it, it's going to detect every pixel and tell you if that pixel is a cloud pixel or not. So in that sense, so let's say you have a very high resolution image, right? So it's going to take quite a while and quite a lot of CPU and memory resource just to label every pixel in a single image. So one of the avenues we've tried lately is to actually do, instead of semantic segmentation, we're trying to do object detection, which means that instead of labeling per pixel, you're just drawing a box around the clouds. Accuracy could suffer in a way, right? Because if you draw a square around a cloud, it's not actually representative of the actual shape of the cloud. In terms of performance, it's really good enough for us to use this. So just to give you a sense of the performance gain that we had. So from 5 to 10 seconds per image, right now we're clocking to around less than a second per image.
Yeah, that's a huge increase. But I'm thinking too, if you're using bounding boxes for clouds, I mean, you could get really unlucky and have a long, narrow cloud that actually had a huge bounding box that obscured most of the image. There could be things like that in that model.
Yeah, I totally agree. So one of the avenues we're going to explore in the future is to actually rotate those bounding boxes. So as you mentioned, if there's like a diagonal cloud, right? If you draw a bounding box there, it's likely that there's so much part of that box that's just not clouds. So what we're going to do is we're going to explore rotating these bounding boxes, probably in various angles, let's say 45 degrees, 30 degrees, 60 degrees, and so on, and try to see if we can fit clouds better using those rotated boxes.
So during the conversation here, we talked about why this is difficult. And one of the things that made it difficult was that we had this sort of top-down view. So we're looking at the world from a satellite platform, from the top, looking down all the time. Does that mean that when this model of yours gets really, really good, will we be able to apply that to different use cases to detect different objects now that it's been trained to detect objects from this top-down view?
Yeah, that's a really good possibility here. And one of the extensions of these models, as you said, is really to detect other objects, not only clouds. In a sense, like clouds are a bigger challenge than detecting other objects. Why? Okay, let's say, for example, you want to detect buildings on satellite imagery. I guess in a way they're kind of easier because one, they're very well defined in their shapes, right? They're almost always rectangular. But for clouds, they could be very dispersed. They could have very irregular shapes and so on. So I think if we can pull off a cloud detection model, then it's going to be slightly easier, work for us to build more models that can detect other objects, such as maybe cars, planes, buildings, and so on.
I've got a couple of questions here, but the first one is, this seems like it's the first step to all that, right? Because if we can't detect if there's something obscuring our view of the surface of the Earth, then we definitely can't run our car detection algorithm or our building detection algorithm. Why haven't people been focusing on this kind of thing until now?
I guess the nature is just more trial and error these days. The needs of having satellite imagery is probably not as frequent yet as it's going to be in the future. Let's say for now, you're a real estate developer or a city planner, right? You don't need daily images of your construction site or your neighborhoods. You're probably just going to want like maybe a weekly image of that, or perhaps even a monthly image of that, and then you can still do pretty well with those. Yeah, in that sense, it's really because of the trial and error part where, okay, so I want to detect, I want to get a satellite image of this neighborhood here, and then it's very cloudy. Okay, let's try again tomorrow, or maybe let's try it again next week. And it doesn't really matter yet, at least. But the industry as a whole is actually going to this route where everyone is going to need more frequent data. What I mean by that is they're probably going to need satellite images in the frequency of hours or even less than an hour, probably minutes or so. That's when this sort of inconvenience starts to kick in, and people may want to try alternative solutions.
I just want to follow up with the second question that I didn't get a chance to ask before, and that was if there was a natural extension to this, and by extension I mean if you could point this at the next most interesting thing for you to detect, what would that be, and what would it be well suited to?
Sure. There is a technology right now that's very promising. That's going to be very promising for satellite data and for all Earth observation in general. It's called SAR, SAR, which stands for Synthetic Aperture Radar. So the biggest benefit of using SAR data is that it's independent of weather and daylight conditions. So what does this mean? It means that SAR data can actually penetrate through clouds, and it doesn't discriminate between night or day, which is a really big win for everyone. Because right now, we sort of or tend to schedule satellites passing through our areas of interest during daytime, so that we can have a clear capture of that. And on top of that, this also vastly increases the chance of acquiring clear and usable satellite images of the area of interest. There's just so many promising avenues that SAR imagery can do or can be capable of. Finally, I would say like SAR imagery can also be used to detect and even quantify the motions of objects on both, I would say like land and sea. So we call this motion or motion detection.
Okay, and this would be a good candidate for your algorithm because you will have already trained it to detect objects, from the top down, and then we could just apply it to this different spectral band, the SAR band.
That is right.
That sounds really interesting. I've actually heard a lot about SAR data, but I've never really stopped to think exactly why there was so much fuss about it. So I really appreciate you taking the time to clarify that for us.
Oh, you're welcome. A natural extension of this is the question of if SAR data is going to be vastly more useful than optical data, then why is there still a need to do cloud detection if it's going to be obsolete or probably deprecated in the future? The answer to that is really how the conditions of Earth observation are right now. So right now, optical imaging is vastly more than radar imaging at the moment. So I think roughly for every 500 satellites that can offer optical imaging, there are only 50 satellites that can offer radar imaging, and even much less than that for SAR. So there's more like even like a 10-to-1 ratio at the moment, or even more. So there's still a long way to go for SAR, which means that in the meantime, cloud detection is still going to be very important.
Yeah, and I can see once you can detect clouds and you have the option of finding SAR data and optical data, this idea of fusing data sets together, I can see some really, really big wins there.
That is true. Yeah, there's just so many applications that we can still do with satellite images. As I mentioned, like real estate, city planning, even economic or financial applications. Let's say you want to measure, I don't know, like maybe oil tanks. You want to measure the roads. You want to count the cars, the airplanes. You want to count the ships, and so on. And on top of like all of these commercial or aside from these commercial applications, there's also like other humanitarian applications such as like disaster response, where you can detect wildfires and so on, just like the recent ones that happened back in California.
So right at the start of the conversation, we talked a little bit about this idea of programmatic access to satellite data, and you described the way it looked today. It sounded really slow and clunky. Would you mind sort of just shooting us forward 5 years in the future and telling us what this might look like in the future? So, of course, we're assuming that you build a stable, reliable algorithm here. You can detect clouds and you can do it quickly. What is that going to mean for access to satellite data in 5 years' time?
Yeah. So the number of satellites that are going to be launched to do Earth observation or perform Earth observation is going to grow exponentially in the next few years. A big reason for this is the way that materials or technologies are getting cheaper and cheaper by the moment. And the cost of actually launching a payload up in the atmosphere is also getting cheaper and cheaper. So this really drives the exponential growth in the number of satellites that are doing Earth observation. So what does this mean? This means that instead of having to wait for another image or another satellite to pass by your AOI or your area of interest, we could eventually get into a world where there's near real-time access to satellite data. And this speeds up tremendously the value chain and the value creation that we can get from Earth observation.
So that makes perfect sense to me. Out of curiosity, does this mean that everybody is going to need their own algorithm, like the one that you're developing, or is there going to be some sort of central hub where I can go there, draw a bounding box around my area of interest, and say, well, I'm interested in that, and then have this cloud detection algorithm run on the background, pointed at a desired satellite source?
Yeah, hopefully everyone doesn't have to build their own models. Hopefully, I think we're getting there pretty fast. As I mentioned before, the performance or the accuracy of your model depends on the size of your training data, and because of such number of satellites that are growing exponentially, we're also going to have an exponential growth in terms of Earth observation data, which means that eventually we could get way more accurate models, way faster models, and these models don't have to be used by everyone. They could just be like something that seems non-trivial today, but it's just going to be trivial tomorrow. Where whenever you search satellite imagery, it's always going to include a cloud mask or other objects in that image, like by default. So yeah, it's a very exciting and promising future for Earth observation.
Adler, I really want to thank you for taking the time to talk with me today. I really enjoyed the conversation. You've definitely opened my eyes to why this is important for the first thing, and the amount of challenges that there are around this. So it's been really interesting for me personally. I've really enjoyed it. But before I let you go, where can the listeners go to reach out to you? If they have more questions about this, if they want to learn more about your work, or just continue this conversation, where should they go?
They could go visit my LinkedIn page, Adler Santos, just one word, or they could even go to my Twitter account, which is again Adler Santos, just one word. That's also my Twitter username.
Excellent. Thank you so much for your time. Much appreciated.
Thank you so much, Daniel. It was great.
So I really hope you enjoyed that interview with Adler, and I just want to take a few minutes here to mention a few things that really stood out for me. The first thing that I was a little bit surprised about, that is actually that the RGB bands were the common denominator across such a wide number of satellite platforms. So much so that this is what Adler and his team have based their cloud detection algorithm on. For some reason, I just always assumed that the real value in these platforms was all the other different spectral bands that were on offer and building up really complex signatures. And it seems to me that that the visible spectrum was just of less value. But it turns out that that is the common denominator, and that's what they've based their algorithm on. I was also really surprised to hear that access to satellite data is still such a manual process. And this surprises me because there is so much hype around imaging from space, around Earth observation at the moment, with constant, with SpaceX and CubeSats being sent up all over the place, and these different imaging platforms coming online, with this manual process that's in place. So does it really matter that we can take real-time imaging of the Earth if we can't access it in real time? And it's really interesting that it's actually water vapor that's stopping us, that's getting in the way. Too much water vapor in front of these incredibly expensive and complex systems, and in terms of RGB anyway, in terms of the visible spectrum, they become redundant because you cannot see the surface of the Earth. And after hearing Adler's thoughts around SAR data, so synthetic aperture radar, and how that's going to be a game changer, I think that I'll have to do an episode at some stage where we take a deep dive into that, because that sounds incredibly promising. So I'm clearly no expert in SAR data, but I think the magic here would be that we could image the surface of the world through clouds, and we could do the same thing at nighttime. So that sounds really interesting. But again, if you're interested in that, let me know, reach out to me, and I'll try and find an expert to bring on the show and to demystify it a little bit more. So once again, a huge thank you to our sponsor, Landgrid.com. This is your go-to place for parcel data for the US, for property boundary data for the US, Landgrid.com. Check them out. And that's it from me. Thank you so much for tuning in to another episode of the Mapscaping Podcast. My name is Daniel. If this is your first time here and you have not yet subscribed, consider doing so. I produce a weekly podcast, so there'll be a new one out next week. And if you subscribe, that'll just automatically land in your podcast player. Okay, thank you very much for tuning in. Feel free to reach out to me on whatever channel you prefer. And yeah, we'll talk to you again next week. Bye.